The following complex potential set plus 1 over set is used when we are describing the heat flow or fluid flow around a cylinder. In order to describe this in the best way, we use polar coordinates. So replacing set by its polar form r multiplied with exponential function of I theta, we obtain this. So here we have something in the denominator which is we want to remove it and replace it by a real number, so we multiply with the complex conjugate in both the numerator and denominator and obtain this. Using the Euler formula, which is very well known, I hope you already have discovered it. It tells that this exponential value of I theta is just the cosine of theta plus I sine of theta. So doing this, replacing here this guy by the cosine of minus theta, which is the same as cosine of theta, and we have plus I sine of theta, sine of minus theta, which is the same as minus sine of theta. So therefore we get this, and now we can collect all real terms and imaginary terms and obtain this real part and this imaginary part. So this is the real part, which is the potential we are going to use in the description of this fluid flow, and also this imaginary part, which is essential for finding the streamlines. So the streamlines are found when this imaginary part is equal to some constant. So when is this happening? Well, it's for example, if the constant is 0, then we have that sine of theta multiplied with r minus 1 over r should be equal to 0. So therefore sine of theta must be 0, or this r must be equal to 1. So the only way of getting this equal to 0 is that r is equal to 1. So what does this mean? Well, it means that we have a streamline. This is a very interesting streamline, because when r is 1, we know that we are on this boundary, because this circle has radius equal to 1 and centered at 0, and either no theta is equal to 0 or pi, which is on this point, or we are on this part of the boundary. So this means that the boundary conditions are met. We know that we have some streamline around this cylinder, and the cylinder itself is a streamline. So this indicates or proves that this complex potential is the right description, or the right tool for finding the fluid flow around the circle, this cylinder. Okay, we have that the velocity u, which is u1, u2, can alternatively be written as a complex function in this way. We have seen this before, and we have also proved that u can be written as the complex conjugate of the derivative of the complex potential. So if we now find this derivative, which is very easy to do because we have the definition of f of z here, and the derivative with respect to z is of course 1 plus minus 1 over z square. So we have this here, and we also know that this is 0 when we have when z is equal to 1, because then we have 1 minus 1 here. So this shows that this velocity is 0 at these points when z is plus minus 1, because then the square of z is equal to 1. So, well, we can also find the expression for this velocity field. We have already seen that u is equal to the complex conjugate of the derivative of the complex potential, and the derivative is this function. And well, we can do as we did earlier, multiplying with the complex conjugate of the denominator, and we get this, and these two, the product of these two guys is just equal to the absolute, the square of the absolute value of these two factors. So we get this, and well, here we can replace z square by we have seen this earlier, that the z square can be written in terms of x and y in the following way, and by conjugating it, and the same in the denominator. Here we have that this is just the this absolute value is just the sum of the squares of x and y. So taking the conjugate of this, we obtain this. So here we can do some elementary manipulations. We know that this is the real part, and this is the imaginary part with this minus inserted, and we obtain trivially this. So what we have found now is that the derivative of this complex potential conjugated is equal to this real part plus I multiplied with this imaginary part. And since this is equal to the velocity u, we know that the real part must be equal to u1, the x component of the vector, of the velocity vector, and here we have u2, the y component of the velocity vector.